Today we're going to look at a pretty cool infinite sum involving the inverse tangent function and Fibonacci numbers. So let's quickly recall that the Fibonacci numbers are a recursively defined sequence with seeds 0 and 1, and the recursion where one term is equal to the sum of the previous two. But observe from our sum up here, we'll need to know negative values or negative indices of these Fibonacci numbers, which are a little bit non-standard. And so let's see what we really mean about that. And we'll get that by looking at this chart of values of n, the index, and the Fibonacci numbers. Notice I started with my seeds here. So f0 is 0, f1 is 1. And then just to move rightwards, I'll sum the previous two boxes to give me the next box. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. So that means that f sub 5 is 5, f sub 4 is 3, f sub 3 is 2, so on and so forth. And now let's go backwards. But here we've got to answer a question. So we need this number plus 0 to be equal to 1, because this 1 here has to be the sum of the previous two. Of course, that means we have to have a 1 here, meaning that f sub negative 1 is 1. Then this number right here has to be added to 1 to give us 0, so this has to be negative 1. And then this number right here has to be added to negative 1 to give us 1, so this has to be 2. And that's how you could extend this to the left infinitely, as well as the standard rightward extension. Okay. We're also going to need some tools which we've developed on the channel before, in addition to one more which we'll derive quickly. So the first is this sum formula for the inverse tangent. We have arctan of x plus arctan of y is equal to arctan of x plus y over 1 minus xy. And then we've got this thing which is a slight generalization of something called Cassini's identity, which says that fn minus r times fn plus r minus fn squared is minus 1 to the n plus r times fr squared. And then finally, this thing that relates negative index Fibonacci numbers and positive index Fibonacci numbers, which says that f sub minus n is equal to minus 1 to the n plus 1 f sub n. Now we can prove this by induction. Notice our base case is taken care of with our chart here. So we just need to make an induction hypothesis. So let's suppose for some k may be bigger than or equal to 0, we have f sub minus k is equal to minus 1 to the k plus 1 f sub k. And now we want to consider the next case. So let's consider f sub minus k plus 1, like that. But notice that's obviously equal to f sub minus k minus 1. And then by the Fibonacci recursion, we can rewrite that as f sub minus k plus 1. And then minus f sub minus k. So that's really clear. If you move this minus f sub minus k to the other side of the equation, you'll see that we have one term is equal to the sum of the previous two. And now we'll apply our induction hypothesis to the right-hand side. Notice here I'm really using strong induction. So we're actually not assuming just this, but we're assuming this and the previous case. That means technically we need two base cases, but notice our chart takes care of that, so we're okay there. So anyway, we'll apply the induction hypothesis to this right-hand side. And notice here, this will give us minus 1 to the k, and then f sub k minus 1. And then minus 1 to the k plus 1 times f sub k. Okay, great. But now notice that we can factor a minus 1 to the k out of this, and we'll be left with fk minus 1 plus fk, just like that. But then we can replace our minus 1 to the k with a minus 1 to the k plus 2, and then here we have f sub k plus 1. That's obviously because minus 1 squared is 1. So let's observe here that we've done exactly what we need to prove this identity down here by induction. Now that we've got everything taken care of, we can focus on our sum. Okay, so now looking carefully at our sum, we're summing over all integers n the arctan of 1 over f sub 3n minus 1. Okay, so the first thing to do here is going to be to extract the n equals 0 and the n equals 1 term. So let's do that. So I'll just put maybe up here that I'm extracting the n equals 0 term here and the n equals 1 term here. So the n equals 0 term will be the arctan of 1 over f sub minus 1. And the n equals 1 term will be the inverse tangent of 1 over f sub 2. Okay, but then now we're going to split off into the positive sum and the negative sum. I should say the positive indexed sum and the negative indexed sum. So now we'll have plus the sum as n is less than or equal to negative 1. Notice that takes care of everything to the left of n equals 0. And then we'll have our inverse tangent of 1 over f sub 3n minus 1. And now we'll have also the sum as n is bigger than or equal to 2 of the inverse tangent of the same thing, 1 over f sub 3n minus 1. Now I'd like to make an observation from my chart over here, and that is f sub minus 1 is 1, so we can replace that with arctan of 1. F sub 2 is also 1, so I can replace that with the inverse tangent of 1. But then it's well known that the inverse tangent of 1 is pi over 4. That's because tangent of pi over 4 is 1. So we have pi over 4 plus pi over 4 giving us pi halves. So we've got pi over 2 there. And now the next little thing that I'm going to do is re-index each of these infinite sums that are left over. I'm going to take this first one and I'm going to replace every n with a minus n. So that's going to give me the sum as n is bigger than or equal to 1 of my inverse tangent of, let's see, 1 over f sub, and this is going to be minus 3n minus 1, because I replaced n with negative n. And then what do I have for this next bit? Well, I'm going to have to reindex that as well. And now I'm going to reindex this by replacing every n with n plus 1. Now that's going to give me this sum as n is bigger than or equal to 1. That's going to move my starting point a little bit. And then I'll have my inverse tangent, so arctan of 1 over f sub 3n plus 2. Okay, cool. And now I'd like to observe that I can use this last identity down here relating the positive and negative indexed Fibonacci numbers to rewrite this as, well, let's see, what is it going to be? Minus 1 to the 3n. So it's really minus 3n minus 1 plus 1, but the minus 1 plus 1 will cancel. And then after that, we'll have our inverse tangent of 1 over f sub 3n plus 1. Then I have to do one other little simplification here, and let's observe that minus 1 to the 3n is the same thing as minus 1 to the n. I think that's pretty clear because the 3 is not going to change the evenness or oddness of that 3 times n. So now let's start putting this together. So we have pi halves. Now we're going to have that is added to the sum as n is bigger than or equal to 1 of, so I've got my minus 1 to the n, and then my arctan of, let's see, that's going to be 1 over f sub 3n plus 1, and then plus the inverse tangent of 1 over f sub 3n plus 2. And now next up, I'm going to break this into even and odd values of n. And I'm going to simply do that by keeping my sum as n goes bigger than or equal to 1, but then I'll have an object like this where n is replaced with 2n, and another object like this where n is replaced with 2n plus 1. That'll take care of my even terms and my odd terms. And I should have said 2n minus 1 there. So let's see what that's going to look like. So here we'll have this is pi halves, and then plus, so our sum is still n bigger than or equal to 1. And then let's do my even terms first. So all the n's are going to be replaced with 2 n's. Of course, that means that this term right here will always be positive 1. And here we're going to have the inverse tangent of 1 over 6n, or f sub 6n plus 1, and then plus the inverse tangent of 1 over f sub 6n plus 2. Okay, so that's going to be my even index terms. Now let's look at my odd index terms, where I'm replacing all of the n's with 2n minus 1. Of course, that means my negative 1 to the 2n minus 1 is going to be a negative 1. So that means I'm going to have a minus sign, and then I'll have my inverse tangent of, and now I've got to replace here n with 2n minus 1. Notice that's going to give me 1 over f sub 6n minus 2. Then I'm going to do the same thing with my other term, replace n with 2n minus 1, and that's going to give me a plus the inverse tangent of 1 over f sub 6n minus 1. Okay, cool. So now let's bring this big sum up to the top, and then we'll do the last couple of steps. Thanks for sticking around this long into the video. If you're enjoying the video, make sure and hit the thumbs up, and if you're not yet subscribed, think about subscribing. It really helps us out. Okay, so this is what we left off on the end of the last board. I'd like to observe that I've moved some things around a little bit. I put the f sub 6n minus 1 and plus 1 terms next to each other, and the same thing with the 6n plus 2 and 6n minus 2 terms. Also, I use the fact that the inverse tangent is odd to bring that minus 1 inside. Now I'm going to use, let's see, it's this first rule here, this arctangent sum formula. So let's see, I'll have pi halves and then plus the sum as n is bigger than or equal to 1. And now putting these two together, and I'm going to skip a little step where we find a common denominator and add the numerators and the denominator inside of this right-hand side here. It's a pretty easy calculation. And what you end up with is f sub 6n minus 1 plus f sub 6n plus 1 over f sub 6n minus 1 times f sub 6n plus 1, and then minus 1. Okay, cool. Now we're going to do something similar over here, and that's going to give us this inverse tangent of, and now we're going to have f sub 6n minus 2 minus f sub 6n plus 2 over f sub 6n minus 2 times f sub 6n plus 2, and now it's going to be plus 1. So we're left with something like that. And now I'd like to observe the following, that the denominators here can be evaluated using this Cassini identity over here. In fact, what we're really doing here is moving the term over here on the left to the right-hand side of the equation and the term on the right to the other left-hand side of the equation. And so when all is said and done, we'll see that this bit right here turns into f sub n squared. And then likewise, this bit right here will also turn into f sub 6n squared. I think I said n squared here, but I meant 6n squared. So we've got something like that going on. Then, well, what about the rest of this? Well, what I'd like to do here is take this f sub 6n minus 2, and I'm going to write that as f sub 6n minus f sub 6n minus 1, using our recursion just rewritten a little bit. And then this f sub 6n plus 2, and I'm going to write that as f sub 6n plus f sub 6n plus 1. So something like that. Now let's rewrite this whole thing with those simplifications. So we've got pi halves, and then my sum over all positive integers. And then I have my inverse tangent here, and then I'm not changing the numerator. 6n minus 1 plus f sub 6n plus 1 over f sub 6n squared. Then here I'm going to have plus the inverse tangent of, now I've got f sub 6n squared again in the denominator. And then what do we have in the numerator? Well, let's notice that my f sub 6 n's cancel, and then I'm going to have a minus f sub 6 n minus 1 minus f sub 6 n plus 1. But now let's observe that the arguments of each of these inverse tangent functions are exactly negatives of each other. But because we have an odd function in the inverse tangent, I can take this minus sign and simply factor it out. But now it's pretty clear that these two terms are going to cancel, meaning that when all is said and done, we only have one thing left, and that is this pi over 2. And that's a good place to stop.